Welcome back to the deep dive. I have to say, looking at the stack of research you pulled for us today, I had a moment where I had to check the dates.
Oh, yeah.
Because honestly, some of this reads like it was ripped straight out of a science fiction novel set, I don't know, 20 years in the future.
It does feel that way, doesn't it? But everything in that stack is grounded in very, very recent reality.
We're talking about a potential changing of the guard here.
Yeah.
For the last 50 years, the entire digital world, I mean, from supercomputers to your toaster, has been built on silicon.
It's the bedrock.
It is the bedrock of the modern age. But according to these reports, that foundation isn't just cracking, it's being replaced.
Yeah.
We're looking at the end of the silicon age and the rise of materials that sound like they belong in a lab's restricted section.
It's a massive shift. I mean, we aren't just talking about a faster chip or a slightly better phone. We're talking about changing the fundamental physics of how we compute.
Okay, so our mission for this deep dive is to unpack this specific wave of reports.
Yeah.
And it's interesting, a huge chunk of this is coming out of Chinese research institutions.
Mm-hmm.
We need to figure out what these new materials are. We've got bismuth and molybdenum on the list, and why silicon is suddenly getting kicked to the curb.
And, ultimately we need to answer what this means for the legendary Moore's Law.
Right, so walk us through the sources first. What are we looking at?
So I've pulled a pretty diverse mix to give us the full picture. We have the heavy technical papers from journals like Nature and the IE.
The hard science.
That's where the hard science lives, yeah. Then we have specific lab reports coming out of Peking University and Beihang University detailing these new prototypes.
Okay.
And to balance the academic side, I've included industry analysis articles that are discussing production timelines. Some are claiming we could see this tech hitting production lines as early as 2025 or 2026.
Which is, frankly, wild. In the semiconductor world, 2026 is practically next week.
It really is.
But before we get to the future stuff, I think we need to ground this. I'm looking at my laptop right now. It runs fine. Silicon has been king of the hill for decades. Why are we trying to replace it? What is the actual problem here?
It's the problem that has been looming over the entire industry for, the last decade? We've hit the wall of Moore's Law.
Okay, well, let's unpack that. Moore's Law. That's the idea that computers just get twice as fast every 2 years.
That's the shorthand version, yeah.
Yeah.
But it's important to remember, Moore's Law wasn't. It wasn't a law of physics.
It was an observation.
It was an economic and technical observation made by Gordon Moore back in 1965. He just noticed that we could roughly double the number of transistors on a chip every 2 years by, just making them smaller.
Shrink the transistor, pack more in, get more power. Simple.
Ideally, yes. And for a long time, it was that simple. But you can't shrink things forever. Eventually, you run out of space.
I saw a great analogy in one of the analysis pieces for this. They compared the chip to an elevator.
That is the perfect way to visualize it. For years, to get more work done, we've just been shoving more people into that elevator. But now, the elevator is packed, shoulder to shoulder.
You can't fit anyone else in.
You physically cannot fit another person inside without crushing everyone. And in this case, the people are the transistors. We're now making them at 3 nanometers wide.
And just for scale, a strand of human DNA is what, about 2.5 nanometers?
Exactly. We are building machines at the scale of genetics.
That's just mind-blowing. But here's the part that really got me. When you get that small, the rules of physics actually start to break, right? It's not just about running out of floor space.
No, it isn't. This is where silicon betrays us. We run into a phenomenon called quantum tunneling.
Which sounds like something out of Star Trek. Captain, we're experiencing quantum tunneling.
It sounds exotic, but it's a real headache. I mean, think about what a transistor is. It's a switch. On and off. To work, it needs a barrier to stop the electrons when it's off.
Right. If the switch is off, no power should flow.
Precisely. But at 3 nanometers, the wall that stops the electrons is only a few atoms thick.
So it's too thin to hold them back.
Think of it like a house party.
I like where this is going.
You lock a bedroom door because you don't want guests in there. In our world, a locked door works.
Usually.
But in the quantum world, if the wall is thin enough, the guests, the electrons, they don't even need the door. They just walk right through the wall, like ghosts.
So your off switch isn't really off.
It's leaking constantly. And in electronics, leakage means heat. Massive amounts of waste heat. This is why your phone gets hot. Silicon simply cannot hold back the electrons at that scale.
So the elevator is full, and people are phasing through the walls. Not good.
Yeah.
So we need a new material, a better wall. And this is where that research from Peking University comes in.
It is. This is the first big breakthrough. They're proposing a move away from silicon entirely, for the transistor channel at least. They've built a prototype using bismuth oxyselenide.
Okay, let's break that down. Bismuth oxyselenide is a bit of a mouthful. I remember bismuth from high school chemistry. It's in Pepto-Bismol.
That's the one, the pink stuff. But here they're using its properties to build something called a 2D GAFET.
Okay, GAFET, gate-all-around field effect transistor. But what does the gate-all-around part mean? Why is that important?
Well, imagine a garden hose. That's your channel where electrons flow. In older chips, the gate, or the switch, just sat on top.
Okay.
Gate-all-around is like wrapping your whole hand around the hose. You have perfect control. You can squeeze it from all sides and shut off the flow completely.
So that solves the leakage problem.
It helps immensely. But the real magic here is the 2D part. Bismuth oxyselenide is a 2D material. It naturally forms in layers that are atomically thin and incredibly smooth.
And why does smooth matter for electrons?
Friction, or, well, resistance. In silicon, at these tiny scales, the surface is atomically rough. It's like driving a Ferrari on a dirt road full of potholes.
You can't go fast no matter how good the engine is.
And bismuth oxyselenide is the paved highway. In the Nature paper, they compare it to superconductor-like behavior. Now, to be clear, it's not a superconductor, but the resistance is so low, electrons just flow almost effortlessly.
The numbers in that report were staggering. They claim speeds 40% higher than a standard 3-nanometer silicon chip.
40% is a generational leap. Usually companies fight tooth and nail for, 10 or 15% a year? This is huge.
And it used less energy, too.
10% less energy consumption. So it's significantly faster and burns less battery. That's the holy grail.
It is. So bismuth gives us speed and efficiency. But there's a second material that keeps coming up. Molybdenum disulfide.
Yes, molybdenum disulfide, or MOS2. This connects to the other big problem with silicon density.
We're back to the crowded city.
Exactly. We build chips today like urban sprawl, a massive, flat suburb of single-story houses.
And the commute times get too long.
Right. So what do you do when you run out of land in a city?
You build skyscrapers.
You go vertical. Now, they've been trying to do this with silicon, but it's brittle, it's thick, and processing it needs incredibly high temperatures. You try to build a second floor, you basically melt the first one.
Which seems counterproductive.
Just a bit. Molybdenum disulfide, like the bismuth compound, is a 2D material, a monolayer. So you can stack these layers on top of each other without destroying what's underneath.
You can build a skyscraper of computing power.
Precisely. A massive increase in density without the thermal nightmare of silicon.
And this links back to that timeline that shocked me. The reports mentioning mass production starting in 2026. Is that realistic?
It is incredibly aggressive,
Yeah.
but the sources note something important. These materials might not require a complete reinvention of the wheel.
Knitting.
The report suggests that these new transistors can be integrated into existing circuit designs. If they can slot them into the final assembly stages, it becomes an evolution, not a hard reset.
That makes the economic case a lot stronger.
Much stronger.
So we have bismuth for speed, molybdenum for density. But there was a third innovation in the stack from Beihang University that I think is the most sci-fi of them all.
Ah, yes, the Beihang research. It's fascinating because they aren't just looking for a new chemical, they're looking for a new logic.
A new way for a computer to think. They call it a hybrid AI chip.
Right. And the hybrid part isn't gas and electric, it's binary and stochastic computing.
So binary is what we all know. Ones and zeros. True or false?
It's deterministic. You ask a computer what's 2 plus 2, it will calculate exactly 4.
Which is what I want for my bank.
For a bank balance, absolutely. But think about AI. Image recognition? Your brain doesn't calculate the exact coordinates of every whisker to know it's a cat.
No, I see a cat. It's a pattern.
It's a probability. Your brain says there's a 99.9% chance this is a cat. That's stochastic computing. It deals in probabilities, not absolutes.
So this new chip does both.
Yes, it keeps the binary part for the exact stuff, but it offloads the AI pattern matching to a stochastic architecture.
Why does that matter?
Energy, the power wall. Doing probabilistic work on a precise binary machine is like using a sniper rifle to swat a fly. It works, but it's massive overkill. Stochastic computing is the fly swatter.
Good enough accuracy for a fraction of the energy. And the most surprising part was that they're using older tech to build it.
Yeah, 28 nanometer and 110 nanometer processes.
110 nanometer. That's practically antique. That's tech from the early 2000s.
It is, but because the architecture is so efficient, they don't need the tiny transistors. It's innovation through design, not brute force.
Which brings us to the elephant in the room. Why is all of this bismuth, molybdenum, stochastic chips all coming out of China right now?
Well, necessity is the mother of invention, and in this case, the necessity was created by geopolitics.
The export controls.
Correct. Over the last few years, the U.S. and its allies have placed very tight restrictions on the export of advanced lithography tools to China, specifically the EUV machines you need to make sub-5 nanometer silicon chips.
So they were cut off from playing the silicon game at the highest level.
They were blocked from that path, so they had to find a detour. They couldn't go through the silicon wall, so they're trying to go around it with completely new materials.
It's a massive plot twist. The sanctions were meant to slow them down, but it seems to have forced them to leapfrog into post-silicon research.
It's that Sputnik moment effect. You back a major power into a corner technologically, they tend to pour massive resources into finding a way out.
And we should be clear here, as observers, we're not taking sides. Science is science.
Absolutely. Physics doesn't care about borders. If bismuth oxyselenide works, it works. The whole world will eventually adopt it.
Okay, but we need to pump the brakes. We've been painting a very rosy picture. Faster, cooler, cheaper, coming in 2026. Is this too good to be true? What are the catches?
Oh, there are significant catches. The biggest one is the gap between a lab and a factory. It is one thing to make a perfect bismuth transistor by hand in a clean room. It's another thing to print 1 billion of them on a wafer.
What's the specific hurdle?
Defects. We talked about these materials being atomically thin. That's their strength, but it's also their weakness.
Fragile.
It's that there's zero margin for error, a single atom out of place, a single wrinkle in that 2D sheet, and the whole chip could fail.
It's like trying to lay down a sheet of saran wrap across a football field without a single air bubble.
That's a perfect analogy, and doing it millions of times a day. It's a manufacturing nightmare. We have 50 years of experience polishing silicon. We're starting from scratch here.
And what about the materials themselves? Bismuth and molybdenum aren't as common as sand.
That's the other issue, supply chain and environment. Bismuth is a byproduct of lead and copper mining. Scaling this up means a massive increase in those operations.
We might be trading an energy problem for an ecological one.
It's a very real possibility. We have to look at the total life cycle cost.
And that 2026 timeline. Do you buy it?
I'm skeptical. Production can mean a lot of things. It might just mean a pilot line running low volumes, maybe for a niche military chip.
So I shouldn't expect the iPhone 17 to run on a bismuth chip.
Probably not. Consumer electronics need massive scale and proven reliability. I think we're looking at a longer horizon for the gadget in your pocket.
So, zooming out, we started by asking if this is the end of the silicon age. What's the verdict?
I think end is too strong. Evolution is better. Silicon isn't going to vanish overnight, but its monopoly is ending. We're moving into an era of, well, they call it system technology co-optimization.
That's a fancy term.
It just means we stop looking for one magic material. We might see chips with the silicon base, a layer of molybdenum for memory, and a bismuth channel for logic, all using a stochastic architecture for AI.
A mix and match approach.
Exactly. We're expanding the recipe book.
So for the listener driving to work right now,
Yeah.
why does this matter to them beyond just faster phones?
It matters because of what that speed enables.
Yeah.
Think about the limitations you face today. You want to ask your phone a complex question, but it has to send that data to a server farm somewhere, process it, and send it back.
There's a delay. And if you have no signal, you have a dumb brick.
Exactly. With these post-silicon low-power chips, you could run a ChatGPT-level AI locally, right on your device.
It could anticipate what you need before you even ask.
It learns your habits in real time. It becomes a true digital extension of you without needing a cloud. It breaks the tether. That is the consumer revolution.
I love that. But I want to leave everyone with a thought that's been stuck in my head since we talked about the hybrid chip.
The stochastic one.
Yeah, we've always drawn a hard line between computers and brains. Computers are binary, rigid, precise. Brains are messy, probabilistic, fluid.
And now we're purposefully building chips that act like brains.
Exactly. If we start building computers that guess and deal in probabilities, are we still building calculators? Or are we starting to build synthetic minds?
That is the ultimate question. And if the hardware starts mimicking biology, the software won't be far behind. The line is definitely blurring.
Something to think about next time your phone autocorrects you. That's it for this deep dive into the post-silicon world. Thanks for listening.
Stay curious.
See you next time.